So that day we have given the statement and this statement of Raleigh's theorem and that of mean value theorem. Today we will take up the exercise therein. Just slide, let me adjust it. Okay. So now today we will take up the questions of this Raleigh's theorem and that of mean value theorem. Exercise 5.8. It is now question 1. It says verify Raleigh's theorem for the function fx is equal to, yes, this is your function, this is your x square plus 2x minus 8 and x is the element in the enclosed interval minus 4t. So this is your polynomial. You had to verify the this thing whether Raleigh's theorem holds therein or not. Now see, first let us see whether the conditions of this Raleigh's theorem they are holding true here or not. So first condition is that the function should be continuous in the closed interval minus 4 to 2. This function is a polynomial and we have already learned that a polynomial is continuous throughout its domain. And what will be the domain of this polynomial? The entire real line. This we have already learned earlier. So this is continuous and f dash x, that is the first derivative, will be nothing but 2x plus 4, which is also so it is differentiable in the open interval minus 4 to 2. So that condition is also satisfying. Now the third condition, which requires that the value at the minus 4 and 2 there should be equal. So let us calculate the value at minus 4. So minus 4, it will be minus 4 whole square plus 2 into minus 4 minus 8. So it will be 16 minus 8 and minus 8. So the value turns out to be 0. Let us calculate the value at 2. So at 2 it is 2 square plus 2 into 2 minus 8. So it is 4 plus 4 minus 8. So it is satisfying. So fine it is, because 8, this is also 0. So both this third condition is also satisfying. That is f minus 4 is equal to f2. So all the three conditions of Raleigh's theorem, they are satisfying over here. So we have to now verify it. So verification demands what? That in between somewhere in the open interval minus 4 to 2, there will lie a point C where the derivative will be equal to 0. So quickly, so this derivative 2x plus 4, let us put it equal to 0. So what this value will be giving me is minus 4 by 2, that is minus 2. And minus 2, see, lies in the open interval minus 4 to 2. So the verification of Raleigh's theorem holds good. Now question 2. So here the question 2, please see what it says. Examine if Raleigh's theorem is applicable to any of the following function. Can you say something about the converse of Raleigh's theorem from these examples? Okay. Let us see. Fx is equal to, please see, fx is equal to greatest integer function x, and the interval given is x is the element from in the closed interval 5 to 9. In the closed interval 5 to 9. Now here see, this is the greatest integer function. Obviously see, we have learnt that this greatest integer function is not continuous at the integral values. That is, neither it will be continuous at 5 nor it will be continuous at 9. So these are the 2 points where the continuity doesn't hold good. That is the end point. What is the reason for it? Because see, what is, see, if you look in, what is the value of f5? Please look in. So f5 will be precisely greatest integral value of 5, that is this thing, and this is nothing but 5. But now see, for checking the continuity, what you need to show is that limit x tending to 5 plus, let us see what it is, greatest integer 5 plus when you are approaching here. So this will give you what value? It will give you always 5, because once you are here, suppose this is 0 and then you are on the right side, then it will be 5. But the limit of left hand limit, what it would be? It would be, see, 5 minus, when you are calculating it, it will be 4. It would be 4. So this is left hand limit and right hand limits are not equal. As such, the question of continuity doesn't hold good, because if at all it is continuous, then at least both left hand limit and right hand limit should be equal, and both of them should be equal to what? Functional value. So this is the reason that here for the greatest integer function, the Raleigh's theorem won't hold good in this particular case. Let us take the part B here. In part B, what they say, the function given is what? Again see, greatest integer, but only the interval they have changed in. Only the interval they have changed in, minus 2 to 2. Obviously see, if you take, whether you take minus 2 or you take 2. Let me take minus 2. So at minus 2, see, it won't be continuous, because limit x tending to minus 2 on the right side, it will be, fx will be what? It will be nothing but limit x tending to minus 2 plus, and this minus 2. Okay, so what it is? It will be minus 2 only. Minus 2 only. And see, it's simple to see. It is 0, it is what? Minus 1, it is minus 2. When you are on the right side of it, then see what is the greatest integer which is less than or equal to x. So when you are this side, so it will be obviously minus 2. But when you are on the left side, then see limit x tending to, when you are calculating minus 2 from the left side, that is minus 2, then it will be what? Minus 3. So both left hand limit, right hand limit won't be equal, and as such the function won't be continuous in the closed interval minus 2 to 2. Therefore the question of verifying Raleigh's theorem doesn't holds good. So this is second thing. Third, see, in the third portion, let us see what, in the third part, what it says. Yes. In the third part, it says that function given is your fx is equal to, this is your third part of question number 2. Question number 2, third part. Fx is your polynomial function, x squared minus 1. For closed interval, x is the element of what? Closed interval 1 to 2. 1 to 2. Okay, so now please see that I think it's visible. Okay. Bhavesh sir, it is visible. I think the entire board is visible.
Yes, sir.
Okay. Now fx is equal to this thing. What is this polynomial? Polynomial function you have already learned that it is throughout its domain, that is throughout its real life, it is continuous. So obviously it will be continuous in the closed interval 1 to 2. It is differentiable as well. F dash x, it is what? 2x minus 1. So again see, it is differentiable in the open interval of this 1 to 2. And then let us calculate for the third condition. What is f1? f1 is 1 square minus 1, 0. What is f2? It is 2 square minus 1, so 3. So here f1 and f2 are not equal, and that's this Raleigh's condition. The third condition of Raleigh's theorem is not holding in this case of x square minus 1. As such, we will not justify it. Now, see, there is a very important question which has been asked here. That this is an important question. Here in all these three problems, what you had to say, something about the converse of Raleigh's theorem from these examples. Now regarding the converse part, please see to it. Now, see in the first case, when you were having the greatest integer function, and the interval given was what, say it was 5 to 9 in the first example. X was 5 to 9. Okay. Now here see, if you look in the interval 5 to 6, open interval, or in 6 to 7, or from 7 to 8, or from 8 to 9. If see any of these intervals you take in, and therein if you see what is and find the value of f dash x, then it will be always 0. It will always be 0. For the obvious reason, suppose you are taking the interval this 5 to 6, then what is the value here? Here greatest integer function, when x is belonging to open interval 5 to 6, then greatest integer function will always be equal to 5. And therefore, your fx is a constant function, and f dash x of a constant function, you know it is 0. So point is that, see, you are getting an intermediate point where the derivative is 0. But then, see, neither the function is continuous in the closed interval, because you have already seen that at the endpoints, at the integral value, this greatest integer function is not continuous. And as such, when it is not continuous, and moreover it is also not differentiable at this integral value. The greatest integer function will not be differentiable for the obvious reason, because if you look in the geometrical interpretation of this derivative, then what it says, that it gives you the slope of the tangent. Now see, suppose I plot the curve of this between 5 and 6. Suppose this is 5 and 6. And exactly at 6, it will be like here. It is between 5 and 6, it will be 1, 2, 3, 4, 5. So it will be like this. Between 5 and 6, it will be like this. This point will be here. And from 6 here, it will go like this. This 6 here, exactly at 6, it will be like this. So this is the point. And exactly if you look in at 6, then what on the right side, the tangent will be this line itself. And on the left side, the tangent will be this line. So derivative will not also exist at any of these integral values. So point is that though the derivative is 0 in some intermediate interval, but still neither the function is continuous nor the function is differentiable, and as such the converse of the Rayleigh theorem doesn't hold good. Please see to it. So converse doesn't hold good, that is the answer. Okay. Now let us see the question number 3 here. They are simple questions provided you have understood the theory part. Question 3, let us see what it says. It says, if f minus 5 to 5, there is a function f from where to where? From minus 5 in the closed interval minus 5 to 5 to r. This is your function. And it is a differentiable function, it has been given. And if f dash does not vanish anywhere, then prove that f minus 5, yes, it's a good question. Then prove that f minus 5 is not equal to f5. What has been given? That there is a function. And this function is differentiable function, okay? And f dash does not vanish anywhere. Please see. Then you have to prove that this is not equal to this thing. This function is differentiable in the closed interval. This obviously means that function will be continuous, because a differentiable function is always a continuous function. This article you have done. If a function is differentiable at a point, then it has to be continuous at that point. If a function is differentiable throughout a given interval, then it will be continuous throughout that interval. Because that this differentiability in an interval is nothing but the differentiability at each point of its interval. So obviously it will be continuous, because if a function is differentiable at a given point, then it ought to be continuous therein. Now see, in question 3, it's a good question. This is your function. From where, what is its domain? Closed interval minus 5 to 5. And what it is codomain? Real, set. Real number set. Now, it has been given it is differentiable. So, first two conditions of the Rayleigh theorem are satisfying, because function is differentiable, it is continuous. And it is differentiable, second condition, in the open interval. So, that is also there. It is closed interval, just hold on. It is not this thing, it is closed interval. Please make this correction. Now, see. Now, what it says is that function, there doesn't exist any point between in the open interval minus 5 to 5 where the derivative vanishes. Vanishes means f dash c is not equal to 0, c being in the line somewhere in the open interval minus 5 to 5. So now see, it says that show that this thing is not equal to this thing. Now suppose if f minus 5 would have been equal to f5, suppose, then what should have, then it would have contradicted your Raleigh's theorem. It would have contradicted your Raleigh's theorem because all three conditions of the Raleigh's theorem would have satisfied. So if you make an assumption that if f minus 5 is equal to f5, then what it means? It means all the three conditions of Raleigh's theorem are satisfying, and as such there should exist a point in the open interval minus 5 to 5 where the derivative vanishes, but it has been given that the derivative doesn't vanish. As such, this assumption that f minus 5 is equal to f5 is wrong. It will lead to a contradiction. So proof is to be given by contradiction method. You will assume that let f minus 5 is equal to f5. This implies what? All three conditions of Raleigh's theorems, all three conditions of Raleigh's theorems are satisfying. Implying that there exists a C element of open interval minus 5 to 5 such that f dash C is equal to 0. And since there doesn't exist any C where the derivative vanishes, therefore this thing will not happen. So this is contradiction. This is your contradiction, and hence the proof is complete. Therefore you can't assume this thing. Therefore this will not be equal to minus 3. Question 4, please look in. Yes, question 4. Please see. Verify mean value theorem if fx is equal to, now you have come to mean value theorem, x squared minus 4x minus 3 minus 4x minus 3 in the closed interval a to b. Where a is 1 and b is 4. Okay, a is 1, b is 4. So it will be in the closed interval 1 to 4. Okay. Mean value theorem. See, once again let us visit the statement. What it says, that if a function is continuous in a closed interval a to b, it is differentiable in the open interval a to b. Only two conditions required in mean value theorem. Then what simply it says, that there exists a C belonging to open interval AB such that derivative therein is equal to what? FB minus FA upon B minus A. This is what they, in the geometrical interpretation, see, this is, we have not given the proof of all these, both this Raleigh's theorem and mean value theorem. So what we need to appreciate right now is that, as I told you, that its proof is to be given at a very high level in your MSc classes when you reach compactness rather. And general metric spaces, then we can also give the proof therein, but that is not beyond your, well beyond your level. So what you need to appreciate is, suppose this is your graph here. So any graph here, like this. Suppose this is your point A, this is your point B, then simply what it says, that this line joining the extreme points, this is what point? A and FA. A, FA, this will have coordinate, this will have coordinate what? B and FB. Then the line joining these 2 points. See, so what it says that on this graph, there will certainly be a point in the open interval A to B where this thing is happening. What this thing is happening, if you look in the geometrical interpretation here, then it simply says that on this graph, there will be a point C where the tangent will be parallel to this line. Which line? Line joining the extreme 2 points. This will happen. So at least one point will exist. There could be many more, depending upon the nature of the curve. But at least one point will certainly exist. And see, this thing you can ensure and you can enjoy and see this is what needs to be given. Let's say you try to come from this point to this point anyway. Whatever. One way is, of course, see, this is straight line itself. This is also one path through which from this particular point, name it P and let this point be Q. But now see, it is not that whimsically you can come from it. I have told you on that particular day that while coming from this, your curve should be continuous, one thing, and not only continuous, it should have tangent everywhere. and which this tangent everywhere on the curve simply means that it is differentiable. And this term, when it is having tangent everywhere, it is known as a smooth curve. So a smooth curve simply means it will not have sharp bends, like in this modulus function you have seen. That in the modulus function, this modulus function is not differentiable at 0. For the simple reason that this line is 45 degrees, this line is again making 90 plus 45 degrees, but this is a sharp line. In the smoothness, see, it should be like smooth. It should be like what you acquire in parabola. So in parabola, see, you have seen, if this figure would have been like parabola something, then it would have been suddenly differentiable because the curve there is smooth. It is not having sharp bends. So this is the difference. And so with such a curve, if you are coming like this, suppose, make sure that it is smooth. And you are coming from this point to this point, then see here at the peak points, everywhere what you will ensure that the tangent is certainly parallel to this thing. And this is precisely what you have done in your Raleigh's theorem. So without taking much more time, because we have already told all these things in quite a good detail when we have taken. And Raleigh's theorem is the generalization of this thing, because if you FB and FA, both of them are equal, then this numerator becomes 0, and therefore f dash c is equal to 0. So all these things you need to know. But regarding the proofs, only the thing which you need to do is that yes, you can do it, that you move from point A to B either way, from any of the paths. There could be infinite paths. But then see, you will always find that at one particular point where you are turning, there see this thing, slope of the tangent will certainly be parallel to the line joining, to the slope of the line joining point P and Q. So this is one, again see, for you people, because the rigorous proof we have not given it to you. So geometrical proof you need to understand, and that too, with quite vividity. Now here in the question number 4, you have to verify this mean value theorem for this polynomial function in the closed interval 1 to 4. Okay, no issues. So for a polynomial, it is obviously continuous throughout the real domain, and obviously it will be. See, all these points you have to write, because when it says that verify this thing for mean value theorem, then you have to tell it is a polynomial function, and polynomial function is continuous throughout the this thing in its domain, and domain is the entire real line. So this thing, and f dash x is what? It is 2x minus 4. So second condition is also satisfying. Therefore, what should happen? You have to now search a point in the open interval 1 to 4 where this thing, slope of this thing, slope of tangent, of course, it will be parallel to what? FB minus FA upon B minus A. Let us see what it is. FB is what? F4 minus F1 upon 4 minus 1. So this is nothing, so what it is, F4 is what? Let us see, 4 is square minus 16 minus 3, okay, and so it is minus 3, and what about this, let us calculate individually, F4, F3, F1, F1 is 1 square minus 4 minus 3, so it is how much? Minus 7, and 1 minus 7, so it is minus 6, okay. So FB minus this value F4 is what? It is, now please we can write F4 minus F1 upon 4 minus 1, its value will come out to be what? Minus 3 minus 6 upon 4 minus 1, 3. So this is minus 3 plus 6, 3 by 3, that is 1. Now please see this value, f dash x is this thing. Now say this is 2. From 2 what you will get? 2x minus 4 should be equal to 1. So x should be equal to how much? This you take this time 5 by 2, that is 2.5, and 2.5 of course well lies in the open interval 1 to 4. So that is the answer. This point 5 by 2 that is 2.5. This is the required point where the tangent will be parallel to this line joining these extreme points. So that is the answer. So this point at x is equal to 5 by 2, the tangent will be, this is the required point of yours. Okay. Read the question, next question please quickly. question number 5. Verify, yes, last question and let me do it. It is question number 5. No, it is last but one. Verify mean value theorem. Again, very simple, hardly anything to do. Fx is equal to how much? X cube minus 5x square and minus 3x in the interval 1 to 3. In the interval 1 to 3, find all points in this open interval 1 to 3 for which f dash c is equal to 0. For which f dash c is equal to 0. So what we need to see, this is a polynomial fx x cube minus 5x square minus 3x. So it is differentiable throughout the domain, not only in the closed interval 1 to 3 but throughout the real life, and it is differentiable also. It's differentiable and it is 3x square minus 10x minus 3. Okay. Now what it says, please see, you have to verify the mean value theorem. Okay, verify the mean value theorem. So for verifying the mean value theorem, first of all, let us find the value of f3. So f3 is what? 3 cube minus 5 into 3 square minus 3 into 3. Okay, so 3 3 9 27, 9 5 45 minus 3 3 9. So how much it gives you? Please check it. 27 minus 45. 5 4 8 18 minus 18 and minus 9. So this is minus 27. F1, it will be 1 cube minus 5 into 1 square minus 3. So 1 minus 5 minus 3. 5 3 8. 1 minus 8, so it is minus 7. Minus 7. So let us calculate this thing, f3 minus f1 upon 3 minus 1. So it is, f3 is what? Minus 27 minus minus 7 upon 3 minus 1, that is 2. So it is 20, minus 27 plus 7. So minus 20 by 2, so it is minus 10. So this is the value of f3 minus f1 upon 3 minus 1, that is minus 10. Okay. Now with this value here, let us see. Yes. Now put this value, 3x square minus 10x minus 3 is equal to minus 10. Bring this side here, 3x square minus 10x plus 7 is equal to 0. Factorize it, 7 3 21. So factors of 21 you have to find it out. So it will be 3x square minus 7x minus 3x plus 7. So what is common here? Nothing. X, 3x minus 7 minus 3x minus 7 and 3x minus 7x minus 1 is equal to 0 is equal to 0. That are the factors. So please see to it. Yes. Now when these are the factors, so one value here is 7 by 3, other value is x is equal to 1. This value x is equal to 1 has to be ignored because this is not lying in the open interval 1 to 3. So the only required value is x is equal to 7 by 3. 7 by 3 is something 2.33 something. So that's the required value and that is the answer. Okay. Last question here. Examine the applicability of mean value theorem for all the three functions given in the above exercise 2. That is greatest integer function. That is the last question here. What it says, what earlier in this question 2, what we have ensured was that its applicability for Raleigh's theorem. Now what it says is that whether this function which has been given in this question 2, and what were the functions? Greatest integer function. So point is that whether the mean value theorem will hold good there, that is the question, please see. So let us see. Okay. Yes. So this is question number 6, please. Yes. Examine the applicability of mean value theorem for all the three functions given in the above exercise 2. So first two functions are what? Greatest integer functions. Now see, in greatest integer function, obviously see, they are not continuous. They are not continuous in any of the closed interval which contains some integral point, because at all the integral points the function is not continuous, and as such the mean value theorem will also not hold good, because provided this thing doesn't, if you, now see, good answer. Here see, in the great case of, there will be two cases, I tell you, there will be two cases. Case one, when your this closed interval contains some integral value. See, first case is when your closed interval AB, closed interval AB contains what? Contains some integral value, Integral value, of course, you understand the integral value or values. It could be more than 2. Like 3, some 3 is there, 4 is there, -7 is there, -11 is there, or if the interval is like -11 to 7, then it will contain some 11 here this side and 7, 18 integral values. So do depending upon what this closed interval is given. Okay, it is closed interval. So whenever it is having some integral values in the closed interval, then of course see, it will not be applicable for the greatest integral functions. For the obvious reason that you can write that at any of integral value, the left hand limit and right hand limits, they are not equal, and as such the function is not continuous. Okay, now there would be a second case when the function is not, when closed function AB does not contain integral values. Any integral value. Now what could this be the example? Please see to it. This is a good question. Suppose I take a interval 1.1 to say 1.9. Now here see, throughout this interval if you look in, see if this is my interval, then throughout here, and my function is greatest integer function, then for this any x here, what will be my value? It will be 1. It will be 1. So my function, whether I write fx is equal to greatest integer function for this thing, or I write fx is equal to 1, that is the same thing. So it is a constant function in this interval 1.1 to 1.9. Okay, so here see the mean value theorem will obviously hold good, because here you take 1.1, the value will be 1. Here you take the function value at 1.9, the value will be 1. So this thing, numerator part, fb minus fa upon b minus a, what it will be? It will be giving you 0 for the obvious reason. fb is what? 1.9 minus f 1.1 upon 1.9 minus 1.1. 1.9 is 1 minus 1 upon whatever this thing, this is 0.8, so 0 upon 0.8 is 0. Okay, so now, and then see what is this function, and so at every point, see this is this thing, the derivative will be 0 because it is a constant function. So in this second case, when your closed interval is such that it is embedded, it is contained between two integral values, between two consecutive integral values, then of course see the mean value theorem will hold good. So this is the answer, and with this see we have finished this exercise. And now we proceed to this last miscellaneous exercise, which contains few good questions and all these methods which you have learned till now in this chapter, they will be covered therein. So now we take up this our miscellaneous exercise here. Miscellaneous exercise of this. Okay. So I take up questions therein because we will be quick enough to finish it. Please open it up of your miscellaneous exercise on chapter 5. So once we finish it, then this entire chapter will be finished. So see, I will be taking only the good ones. I won't be taking all the questions because we have done it. But in case if you want, you can ask it. So the very first question which I intend taking here is question number, question number 5. It is cos inverse, you have to cos inverse x by 2 and upon under root 2x plus 7. And this thing, minus 2 is less than x is less than 2. Okay, so this is the interval where you have to find its derivative. So this is the function. Obviously it is in the quotient form. Both the numerator and denominator, they are exclusively the functions of x. So its derivative dy by dx will be obtained what way? Quotient rule you will have to invoke, because this is numerator, this is denominator. So denominator is squared. So it is under root this thing, so it will be 2x plus 7. And then numerator, denominator 2x plus 7 under root here. And derivative of numerator. Derivative of numerator is what? Cos inverse x by 2. Now it is a function of function. Please see, cos inverse x by 2. So x by 2 you will be putting t. So it is, first you will, t is your internal function here. So first of all you will differentiate cos inverse t with respect to internal function. And then this internal function is to be differentiated with your independent variable x. So it is the product of these two. So this is what perfection you have acquired now in this while obtaining the derivatives of composite functions. So now straight away I am writing it out. But see if anyone amongst you have not understood, then the method would be like this only, that you will put t is equal to what? X by 2, and you will find the differentiable differentiation of cos inverse t, and this is what? Dy by dx. Here will be what? By this composition formula d by dt cos inverse t into dt by dx. Okay, and dt by dx from here is nothing but 1 by 2. So now see, we are writing straight away. So but for the benefit of those who have not done till now, for them it will be 1 by 2 like this. So it is 1 by 2 and minus sign, and then 1 upon under root 1 minus x squared. Okay, 1 minus x by 2, sorry. It is x by 2, please mind it. X by 2 whole square. So x by 2 whole square. Okay, and then minus what? Cos inverse x by 2. Cos inverse x by 2. And let me rub it. Okay, minus, so I am closing this thing here. Minus cos inverse x by 2 and derivative of under root 2x plus 7. Again, see here, 2x plus 7, you will put p. So under root p, derivative of under root p is what? 1 upon under root twice under root p. So under root 2x plus 7 and then derivative of this thing. So this is 2. 2 cancels. Yes, this is under root 2. So this is what you will acquire. Okay, so let us see what this value comes out to be. It is 2x plus 7 to this thing minus cos inverse x by 2 into 1 upon under root 2x plus 7. Okay, so let us take under root 2x plus 7 common here. So this will get multiplied here. So 2x plus 7 into what? Minus 1 by 2 under root 1 minus x square by 4 here, and minus this thing is will fetch you what? Cos inverse x by 2. X by 2 and whole upon what? 2x plus 7 into under root 2x plus 7, that is 1 plus 1 by 2, that is 3 by 2. So see, you can keep it like here if you feel like this is the answer, or if further simplification will not fetch you anything because nothing will cancel here. So this would be the answer. You can keep it here, leave it here. So this is how you would be doing it. Then now let us take question number 6 here. Question 6 here. Okay, it is cot inverse under root 1 plus sin x, 1 plus sin x upon plus 1 under root 1 minus sin x upon under root 1 plus sin x minus under root 1 minus sin x. 1 minus sin x. Now see, you multiply, rationalize this thing, this internal function. So you multiply both numerator and denominator with under root 1 plus sin x plus under root 1 minus sin x, both these things. So here it is a minus b, a plus b. So it will be in the denominator, it will be a square minus b square, and here it will be what? A plus b whole square. So it is cot inverse a square. A square will give you what? 1 plus sin x plus b square 1 minus sin x and plus 2ab under root this thing into under root this thing, that is giving me under root 1 minus sin square x upon this thing. This is under root, this is a minus b and you are multiplying with a plus b. So what you will get a square that is 1 plus sin x minus b square 1 minus sin x. Okay, so this is what you will get it. Now this thing sin x will cancel, 1 plus 1 2, 2 plus 2. So here you are getting is cot inverse 2 plus 2, 1 minus sin square is cos square x, so outside the under root sign it will be cos x only, 1 plus sin x cancels 2. So this is giving you what? This is giving you cot inverse 1 plus cos x upon that all, and this thing you can further be written to be what? Just hold on, 1 plus, oh no, sorry, it is 2 sin x, please see. It is minus 1, so minus 1 will cancel, okay. So 2 sin x you will get it. So it will be here sin x only, okay. So it is 2 cos square x by 2 minus 1, which will cancel with this plus 1 upon sin x, you can write 2 sin x by 2 cos x by 2, and this thing 2 cancel, 1 cos cancels here, so cos by 2, this is cot inverse cot x by 2. So finally you will get x by 2 only. So on simplification what it will fetch you is only x by 2. Once you get x by 2, then whole thing is simple here. Yes, y is equal to this whole lot, it is becoming your x by 2. Cot inverse cot x by 2, so x by 2. Now derivative is simple, y dash is what? 1 by 2 only. So that's the answer. So that's the answer. So this was your question number 6. Let us now try other questions here. There. Yes. Any other question you can check in? Okay, let us take question 7th. It is question 7th here, please see. It is y is equal to log x raised to power log x. Again see, simple. We have done this entire exercise on this thing. It is to be differentiated through, it is to be obtained through differentiation through this logarithmic differentiation we will be taking. So what we will do is that we will be taking the log of both the sides. So log y will be equal to what? Log of log x raised to power log x. So log m raised to power n will fetch you what? Log m log n log x log x. So this is what log y is. Now differentiating both sides with respect to x. So what we will get is d by dx. Please see that you are in the beginning here. Don't rush to the things. D by dx. It is the product of two functions. One is log x, other is log x. So that thing also you will invoke this log x formula. This is first function. This is second product rule you will apply. And here see what d by dy log y is. So here see it will be d by dy log y and dy by dx, y dash. Y dash is what? dy by dx. Okay, let me write dy by dx so that you doesn't confuse here. So this is what first function, that is log x, and derivative of the second. Now what is this thing? This is function of function. Please see, log x. So what you will do? First of all, this log x you will put t, log t you will differentiate with respect to t. So that will give you 1 upon log x, and then see you will differentiate this log x. So d by dx is what? 1 upon x. So 1 upon x. So this x you can get here, plus then log x is your second function into derivative of log x, that is 1 upon x. So this is what you will get on the right hand side. So it is what dy log y, it is 1 upon y into dy by dx. Dy by dx precisely you are looking for, and this is what 1 log x, 1 upon x log x log x log x log x cancels. 1 upon x you can take common, 1 plus log x. Here you will be getting this much of thing, and then see this y, so y dash here will be equal to y. Y is your log x raised to power log x, and into upon x 1 plus log x. That will be the answer. That will be the answer, question number 7. So this is how you will do. See, these are the standard methods. There is hardly anything difficult in it. Only see, now you have to do a little bit of practice, nothing beyond that. So these, now I will move further here. Now I will take question number, okay, which one you want me to take? Similarly, see, you can, any question, 7, 8 is too simple, of course, see, you can do it. 9th, of course, see, if you want, I can take it, but again, see, simple. Okay, 9th question, question number 9. Y is equal to how much? It is sin x minus cos x, sin x minus cos x upon raised to power, same thing, sin x minus cos x. Okay. Yes, and x lies between pi by 4 to 3 pi by 4. Okay. So what you will do? Again, see, you will take the log both sides. Log y is equal to log of this thing. See, I will take log both sides here. So this is log of this thing. Log, and then differentiate both sides. So it is d by dx of this thing and d by dx of this thing. Now this is log m raised to power n, so it is sin x minus cos x. First see this and log of sin x minus cos x. And then derivative of this thing. Now see, obviously it is the product of two functions. This is the first function, let this be the second function. And here d by dx of log y, as obviously, it will be what? D by dy of log y into dy by dx. dy by dx or y dash, you can get it now. And this is equal to this thing. So this is what 1 upon y dash. This is now first function. Sin x minus cos x, you write as such. Derivative of this thing, derivative in the product rule, first function into derivative of second. In the derivative of this thing, what it is? Sin x minus cos x, you will put t log t. Log t you will first differentiate, so what you will get? 1 upon sin x minus cos x, and then you will differentiate this internal function t with respect to x. So it will be fetching you what? Cos x minus, and cos x will give you what? Sin x. So this is this much of thing. First function into derivative second, plus second function is your log sin x minus cos x into derivative of this thing. So this is your cos x minus plus sin x. Okay, cos x plus sin x, or sin x plus cos x. So okay, log of this thing. So okay, so this here sin x minus cos x cancels, and you are left only with cos x plus sin x. And plus, let us see what we get from here. Plus log of sin x minus cos x, sin x plus cos x. Sin. So this is log of sin square x minus cos square x, because a minus b into a plus b, and a minus b is what? A square minus b square. Sin square x minus cos square x, what it gives you? It is okay, and then y dash is y into this thing, y into this whole lot. Y is what? Y is your this sin x minus cos x upon this thing. At place of y you will put your this thing, sin x minus cos x upon sin x minus cos x, and into this thing, cos x plus sin x, and this thing is what? Log this thing. So now what it is? Log sin square x minus cos square x. So you can write this thing is it will be minus, if you take, then it will be cos 2x straight away. Log of minus 1 into cos 2x. Okay, log m into n is what? Log m plus log m, है ना? Log of this thing is what? Just hold on, if yes, it is okay. Log m plus log m, you could have well written it to be. So this is what? Log minus 1, log minus 1 upon log 1. You can write, and then log 2x. So this thing you can well write cos x plus sin x and plus log of 1 plus log of minus cos 2x. Log 1 is 0, so this thing you can eliminate and this thing you can leave with the answer. So this is how you will be doing it. Now next question here. Now we will take some good questions here. We have already done a good amount of questions here. This thing, okay, question 10, let me take it quickly. Question 10, what it says, y is equal to what? X raised to power x plus x raised to power a plus a raised to power x plus how much? A raised to power a raised to power a. Okay. Now here see, if you take the derivative y dash or dy by dx, whatever symbol you want to use, you will use it. So it will be what? D by dx of x raised to power x plus d by dx of x raised to power a. So x raised to power a is what? It is a x raised to power a minus 1 plus a raised to power x. A raised to power x, it is in the standard form, its derivative is what? A raised to power x into log of a, and a raised to power a is constant, so it will be 0. It will be 0. So only the thing is that we have to find the derivative of x raised to power x, which of course we will do separately. Let y1 be equal to x raised to power x, so taking log y1, so it is x log x, and then differentiating both sides. So this differentiation will give me what? D by dx of log y1 is equal to first function into derivative of second plus log x into derivative of this thing, that is 1. So this is what? 1 plus log x. And this is what? D upon dy you will take, and that is will give me 1 by y and dy by dx, dy1 upon dx, which we were looking for. So this is what? 1 plus log x. Okay, and so dy by 1 upon dx is equal to what? X raised to power y1 into this thing, y1 is x raised to power x into 1 plus log x. This value you will put here at the place of this thing, you can put it in this equation, and that will be the required derivative. Okay, so you have to be now careful. You see, only practice at your part will help you. Let me take few more questions here. Okay, this is question number. Okay, now let's take question number 13. Question 10. 11 is almost on the same line. 12 is in the parametric form. Okay, 13. So question 13, let me take it. 11, simple. 13. Y is equal to sine inverse x. Y is equal to sine inverse x plus sine inverse under root 1 minus x square. Sine inverse under root 1 minus x square. Okay. So dy by dx. Dy by dx will be what? Please see, sine inverse x will give me what? Derivative of sine inverse x is what? 1 minus under root 1 minus x square is standard formula. So we will not take it, plus derivative of this thing. Now here this is the function of function. So this under root 1 minus x square we will put equal to t, and then sine inverse t we will differentiate. So it will give me what? 1 under root 1 minus x, this thing, under root 1 minus x square whole square. Okay, please see. And then d by dx of what? Under root 1 minus x square. 1 upon under root 1 minus x square plus and 1 upon 1 and within under root 1 minus, this square is 1 minus x square only, 1 minus x square. So 1 will cancel and you will get x only here, and into dy dx of under root of this thing. The let 1 minus x square you will assume p, so it is under root p, so it is 1 upon 2 under root 1 minus x square, and this derivative of p with respect to x will take you what? This thing, so it is like this. So this is what 1 upon under root 1 minus x square plus 1 upon, see this here 1 got cancelled and this is plus, so you will get x only here. And here in the numerator you are having minus x and upon under root 1 minus x square. This x cancels, and this is 1 upon under root 1 minus x square. This whole cancel and you will get 0. So I stop here. Though I could have taken few more questions. Okay, see, let me finish this page here. Okay, question number 14, let us try. Here, this was question 13, question number 14, that is a good one. But see, this question 14, see, it involves a little bit of trick, see, and then only see you can do it, else it will, and normally you will encounter a little bit of difficulty. Why you will do what, if, say, it is not y, something else you take it, because t is equal to this thing, x under root 1 plus y here, plus y under root 1 plus x, plus y under root 1 plus x. No, it is equal to 0. It is not t. It is, this equation is given here. So this is equal to 0, and you have to find the value of dy by dx. dy by dx. Okay. So here what you need to do is that you take the other side here, x under root 1 plus y. This will be equal to minus y under root 1 plus x. Now squaring both the side. X square 1 plus y is equal to what? Y square 1 plus x. Okay. Now see what we can do here. Let us try to segregate this thing. Okay, well, one thing we can do it, we can differentiate now, assuming that y is a function of x. So this is the product of two functions, this is again a product of two functions. So dy by dx of this thing is what? First function into derivative of this thing, derivative of dy by dx of 1 plus y plus 1 plus y into derivative of x square, that is 2x. 2x. This way, again product of two functions. One is first, this like this, this is second. So first function into derivative of this thing, that is okay, dy by dx of 1 plus x, let me write it like this, plus 1 plus x into d by dx of y square. Okay. Now please see here, it is what? X square. 1 is 0, dy by dx is dy by dx. So it is dy by dx plus 2, 1 plus yx. Okay. Is equal to y square. This is 1, 0, this is 1. So it will be ultimately 1 only. Plus 1 plus x. And now please see, here you have to be careful. You are differentiating with respect to x. So it will be d by y square into dy by dx. So this is your x square y dash. dy by dx, now I am writing y dash, plus 2x plus 2xy is equal to what? Y square, yes, plus 1 plus x, please see, 2y and y dash. Terms containing y dash you put at one place, rest of the terms you take it on the other side. So this is the term containing y dash. So let me take this on the other side and this on this side. So what I will get, 2x plus 2xy minus y square. This will be equal to what? See, 2x plus 2xy, and this thing I am retaining this side, this I am taking other side. So other side it will be what? It will be 1 plus x, 2y, this thing, y dash I will take common from here to here, and minus x square, and this is y dash. So y dash eventually will be what? This thing will come downwards. So 2x plus 2xy minus y square upon this whole thing, and this is what? 2y plus 2xy minus x square. That is the answer. That is the answer. Now see, if you don't square it, then of course you encounter a little bit of difficulty. So see, I stop here because I have completed my 1 hour. You are having some other classes. So thank you.